Last class we discussed about different instrumentation amplifiers strategies. Continuing our discussion about amplifiers, in today's class we will discuss something about some other special purpose amplifiers like audio power amplifier and another general purpose amplifier called Norton's amplifier. These are the two topics that are going to be discussed today. So, let us see the strategy adopted in all these amplifiers. We will see some kind of similarity between this and whatever we have done so far. Right? This is supposed to be a voltage amplifier, okay. And obviously, the input stage is again the good old differential stage, and since it is going to be designed for a specific gain, okay, that is going to be a feedback amplifier. So, it is true that this is a differential amplifier input stage with negative feedback. Okay. So, we have to only identify the various blocks which we have earlier recognized in various amplifiers. So, let us now identify the differential amplifier input stage. This operates with single supply, okay, and self biased. Okay. So, single supply self biased audio power amplifier is what we are going to discuss now. This is the input stage. Okay. You can see here, okay, buffer stage. This is acting as a buffer. Okay. These two will be acting as the buffer, and the primary pair is here, and this particular thing is nothing but the active load. You can see the diode here getting reflected. So, this is similar to the input stage we have earlier discussed, except for a small difference here. Let me make that out clearly. Earlier we have been discussing amplifiers like this. Differential amplifiers like this. There will be a current source here, let us say I naught. The idea is when you apply a voltage V I, right, this will carry I naught by 2 plus, let us say this will be actually plus Gm times V I, this will be I naught by 2 minus Gm times. This aspect we had already earlier discussed, I am sure. Obviously, if we want this Gm to be sort of independent of the active device, then we can put in series with these, okay, physical resistance, that is called emitter degeneration resistance. Okay. That means it becomes a feedback structure. R E. So, what happens, this Gm now gets transformed to V I divided by R E plus small r e 1 over Gm. So, that's all, it gets modified as this. So, this becomes negligibly small, we can design in such a manner that this becomes negligibly small. So, we are able to produce from a differential input voltage a differential current output with a common mode current equal to I naught. See, I naught by 2 plus V I by R A, I naught by 2 minus V I by R A. So, this is nothing but a transconductor stage, you can say, whose conductance value is going to be pretty stable and is going to be equal to 1 over R E. Okay. So, you can say this is a transconductor amplifier, right? Differential input voltage and differential output current. This is obtained by feedback here. Now, it is important that these REs must be the same, okay, in order to produce a common mode DC current. Right. So, how do we do it in an IC? This can be done easily instead of relying upon matching of resistors, relying upon matching of currents this way. The same thing can be effected by removing this arrangement. Okay, this can be now removed, and we will replace this region by a resistance which is 2 RE removed, and then we put here, okay, this current here which is I naught by 2. This current here also equal to I naught by 2. Actually, the earlier this thing should have been 2 RE, I am sorry, right. VI by 2 RE plus, okay, 2 into 1 over GM it was. So, you simply replace this by 2 RE, or actually speaking it is a single resistance, because there is nothing like 2 resistances separately here. Now, this is VI by, let us call it Rx. Is this clear or not? Right. So, this is again a differential arrangement where whatever differential voltage is applied here, corresponding to that only the signal current will be coming. If you have a common mode voltage here, there will be no signal current here. Okay. So, this is the strategy adopted, that is, you have equal current sources, and now this can be used for negative feedback mode of operation, etc. Now, that is why you can now see this is nothing but a differential amplifier which is perfectly symmetric. Imagine this is 25K, 25K with diode to ground, then there is 25K something else, okay, like that. So, this is the place where the negative feedback is effective, okay, to the input stage. You can see if you are applying an input at one point and to the other point you can give the feedback. So, actual input to the amplifier is the current input minus the feedback voltage. Okay. So, current input, okay, minus the feedback voltage can be effective, right. So, that is how you can adopt a strategy like this using emitter degeneration resistance like this. So, it is no different from the differential amplifier, except that, okay, a physical resistance occurs coupling the two emitters. Okay. So, let us now therefore see here, when there is of course negative feedback, DC feedback also from this. So, operating point of those whole structure is going to be determined by negative DC feedback here. Assuming that these two voltages are the same, that means differential input voltage is 0, then what should happen? These two potentials are going to be the same, and therefore, there should be not be any input voltage. So, these two currents will be the same. Okay. These two voltages are same, there is no current in this. So, these two currents are the same. So, if these two currents are the same, what will be this current actually? V 1 diode, okay, 2 diode, sorry, 1 diode, 2 diode, 3 diodes. So, V minus 3 V gamma divided by 50K. That is the current in that. Huh? Pardon? V minus 3V gamma, neglecting the drop in this, right, assuming that the beta of the transistors are high. Okay. V minus 3V gamma divided by 50K is the current. So, what is the current therefore in this? Same, right. So, what will be the voltage V naught? It is going to be 2V gamma, okay, 2V gamma plus the drop in this, which is nothing but V minus 3V gamma divided by 50K into 25K, which is nothing but V by 2, okay, plus 2V gamma minus 3 by 2V gamma, almost negligibly small, 0.5 V gamma, right. So, essentially this is a strategy of biasing the output at almost half the supply voltage, irrespective of the supply voltage. Okay. The bias point is going to be at half the supply voltage, so that output swing is the maximum possible. Okay. This is the audio output stage here, right. So, it should operate for the maximum possible output swing. So, you are now capable of getting the maximum possible output swing by locating yourself at halfway between these two. That is as far as the operating point is concerned. As far as the negative feedback for the signal is concerned, once again we will adopt the same strategy that we have earlier adopted. For signal operation, we can consider that the midpoint of this is can be grounded. Okay. The midpoint of this can be grounded. That means, what is the feedback factor? The 500 ohms and 25K is the feedback factor, which is going to give a gain of, because beta of 1 over 50 or a voltage gain of 50, assuming that the open loop gain is very high. Again, I would like you to now, for the entire stage, now that you know the component values, assuming beta equal to 200, okay, evaluate the open loop gain, okay, as well also the loop gain of the structure, and show that the gain is very nearly equal to 50. Once again, you can find out the input impedance etc. from the same strategy. What is it? It is going to be effectively, what is the input impedance? Effective emitter resistance here. Okay. Essentially, emitter resistance is made up of only 1K and beta, so beta squared, and of course 150K will be shunting that. Okay. Is it clear? The V1, V2 here, right. So, this 150K and this 150K. Now, as far as the output is concerned, once again we have the same push pull stage. You can see intermediate is again the same common emitter stage. So, you have a differential input stage, intermediate, common emitter stage, output stage, which is biased to class AB mode of operation. So, it is the what is that, topology is similar to that of the operational amplifier topology, okay. But it is used for a specific feedback application. Okay. So, you have a compensating capacitor here, once again between the output and input of the intermediate stage for compensating for the frequency instabilities. Then here this is another strategy which is commonly adopted. Okay. This is the NPN stage, and we should have a PNP here, which is a bad PNP, but what is available. So, in order to make it good, you are now adopting the Darlington pair that is possible, connecting what? PNP to NPN. Effectively, the gain of this is controlled by the NPN beta current gain rather than the PNP. Okay. So, this is commonly adopted in most of the output stages, pairing PNP, a bad PNP, with a good NPN, so as to make the drive capability of this, okay, as well as that almost identical current drive capability. Okay. So, we have the provision for the short circuit protection there, for current sensing there, actually some amount of short circuit protection, because this has to operate for higher power here. Okay. So, this can tolerate higher current ratings. So, this is typically one of the most useful audio power amplifiers using single supply, and also you can see here the voltage level required to drive this input is going to be very small. Okay. And the voltage level can go both positive and negative. Okay. Because it is going to be very small, the voltage drive can go slightly negative also, in spite of using, okay, single supply. So, this is a very nice advantage associated with this single supply stage, where, okay, the operation is such that we can go both positive as well as negative slightly by about almost one diode drop negative. Okay. And that much is sufficient, okay, in order to give large output swing. Okay. So, this is LM380 commercial audio power amplifier, which is available here. Okay. In order to make it appear symmetric for the AC purpose, you are grounding the midpoint of this 25 kA, okay, AC wise. So, if you AC wise ground here, okay, this is going to be symmetric as far as AC operation is concerned. Please remember, therefore, the bypass point is brought out here. So, capacitor is connected externally. So, the next topic for today is a very interesting general purpose amplifier called Norton's amplifier or current differencing amplifier. The amplifiers which we have earlier dealt with were primarily dealing with voltage difference, let us say V1 and V2 being the two voltages applied to the two terminals. Then V1 minus V2 was intended to be amplified, that is the difference amplifier that we had discussed. In almost every stage that we had thought of, okay, we had used that concept. Here it is the dual of this. Why use V1 minus V2 as the difference input signal? Instead, we will use the dual, which is I1 minus I2 or I minus, okay, minus I plus, or I plus minus I minus, right. Current differencing. The difference between two currents I1 and I2, let us say IA and IB, okay, is the one which is amplified, fed as input to a transistor base, okay, which is automatically amplified by beta times, etc. Again beta times maybe another transistor stage like that, okay, and appears as an output voltage. So, this is called, okay, Norton's amplifier or current differencing amplifier, CDA. Okay. And this particular thing is manufactured by National Semiconductors, LM, what is the number given? 3900, right, LM 3900, or MC, what is the other number given? Motorola also manufactures, okay, this particular Norton's amplifier, current differencing amplifier. Okay. So, but anyway, the strategy employed is totally different. Let us see what it is. Again, it is the current mirror input stage which is responsible for achieving this sort of current difference as coming as input. We have a current mirror at this point, which is going to get I plus as its input current. This is the diode, okay, and therefore, the current here is going to be always equal to what? Because of this diode, since it is sensing I plus, this current will be always I plus, and since the other terminal gets automatically a current of I minus, the input current into this is going to be, okay, this direction is going to be I minus minus I plus. Please look at it, I minus minus I plus, or current drawn out from it is I plus minus I minus. Okay. So, this is the essential feature of the current differencing. Okay. Obviously, you can see the voltage between these 2 points is very nearly 0, because this is a diode, this is another diode. Okay. So, the voltage is going to be maintained very nearly 0. Okay. Whereas, in the earlier situation, the current input to this stage was 0. Okay. When we had V1 minus V2 as the input signal, okay, it was drawing very little input current. Okay. Here, when we are pumping 2 currents I plus and I minus, okay, it is taking across it very small voltage difference. Okay. Is this point very clearly understood? So, this current difference is going to be beta times multiplied here and further amplified by further transistor amplifiers, okay, and appearing at the output. This is the output stage, okay, making it appear as an output voltage. Okay. So, these are the operating currents of these stages. This is the output stage operating current, this is the intermediate stage operating current. Okay. So, it also has a difference, okay, current differencing input stage, intermediate stage, okay, and an output stage. So, you can see the 3 stages again appearing in this operational amplifier. This, the advantage of this over 741, okay, is this, both these Motorola and National Semiconductor op amps have this advantage, that this performance, because it is current gain that you are ultimately after, this performance of this open loop gain etc., okay, is going to be independent of power supply. Okay. And the power supply can range from pretty low values, maybe, okay, say 5 to 6 volts to 20 to 24 volts range is there. Okay. For the entire range you can use this without its parameters changing much, okay, and use a single supply. Therefore, this is the cheapest amplifier available for most of the single supply applications, okay, and it has become quite popular. Only thing is you have to look at it slightly differently compared to what you were doing earlier. What is this difference? How are we looking at an op amp? Op amp was being used in a negative feedback situation. When it is used in a negative feedback situation, if the op amp gain, open loop gain is very high, then we said the input voltage V1 minus V 2 becomes equal to 0. Okay. It becomes a nullator, 0. Input voltage becomes 0, right. Is this correct? Now, in this particular case, the dual of that should happen. What should happen? The input current difference should become equal to 0. In a negative feedback situation, the two input currents should become equal to one another. If it is used in a negative feedback situation, in the voltage differencing amplifier, the two voltages would have become equal, right, if the gain, open loop gain goes towards infinity. Here, if the open loop gain goes towards infinity, right, the two currents will become equal. Is this point understood? And also, you know that at what DC potential this is going to be, right. Strategically, you can find out that this DC potential is going to be always one diode drop above the ground potential. All that is known to you, okay, at the input. So, it is very easy for normal design of this circuit in a negative feedback environment. Just typically, let us see. So, what does now, okay, V naught become equal to? The current here is going to be VCC, okay, by what? R1, okay, VCC minus V gamma by R1, whatever it is. So, VCC by R1, okay. And this current should be same as that into R2 is the output voltage. This is one way of biasing it DC wise. Okay. So, you can make the bias point at any point you want this to be quiescent point. If you want it to be half, you can accordingly select this. Now, apply signal, AC signal, capacity will couple it obviously, right. So, at this point, so that you can inject whatever current you want into it, right. Then summation of all those currents will flow through this, okay, and appear as signal current at the output. You can extract it again by decoupling it by means of a capacitor. So, the strategy adopted is exactly similar to the voltage amplifier, except in making it operate at a quiescent point, okay, which is of interest to you depending upon the signal swing you would like to have at the output. Okay. So, you can use it in almost all applications wherein you can use the conventional general purpose operational voltage amplifier. So, the symbol for the Norton's amplifier is like this. This is indicating that it is a current, okay, source. This is the current source kind of thing, right. So, it is the current difference which is fed as the input, okay, current difference between these two input currents. So, the other amplifier which we have already touched upon is making use of the principle that we had enunciated in the introductory lecture on translinear principle, that is you can take a differential input current as the input, okay, and keep on amplifying it by using what is called Gilbert's gain cell. Okay. And these cells can be put one over the other. The advantage of this strategy is, once again, what you can keep on amplifying the signal in terms of current alone, retaining the signal swing very small. Okay. It will be only of the order of difference in 2 diode drops. Okay. Maintaining the signal swing very small, you can keep on amplifying the current difference, and when you reach the required power level of current, okay, you can pump it onto the load that you desire. Right. So, this is another strategy. The further advantage of this is useful for wide band applications, because you are dealing with only current swing here and voltage swing is maintained very low. That means capacitors need not be charged. So, in wideband amplifier applications where you want the gain of the amplifier to be stabilized without negative feedback, in all these cases you saw that gain becomes stabilized only with negative feedback, voltage gain. Whereas there in the current amplifiers using Gilbert cell, we saw that the current gain is stabilized already in the open loop mode, okay, in terms of ratio of the operating currents, and therefore, that is another strategy adopted in amplifier design. You can design such, okay, amplifiers as wideband amplifiers, okay, current amplifiers. So, you have so far discussed input current difference as the input to a Gilbert gain cell. If you want a voltage difference to be converted into current difference, you can adopt the same transconductor, okay, using emitter degeneration. Okay. So, that will convert a differential voltage into differential current, and thereafter you can keep on amplifying. Okay. So, transconductor is first used, converted into differential current, and then the Gilbert gain cell is used, which is successively operating at higher and higher currents, and then when you require the highest current difference, that is made to go through again 2 resistors and converted into voltage. Okay. So, these are the varieties of amplifiers available in the market. It is not exhaustive, but it is only representative of the different types that can be made possible. In the next class, we will discuss something about the other active elements necessary for filters, integrators, differentiators, etc. Okay. Not operational amplifiers, but basic active elements themselves can be straight away used. How we can make them become relatively independent of the parameters which are sensitive to temperature, etc. How we can use those active parameters themselves, okay, in a variety of applications.